Hi there! Welcome to your emergency review on linear, quadratic, and rational functions. This review will take you through the entire formative assessment, question by question, so that we can make sure to solidify our understanding of these key concepts. Let's get started. Okay, so from the math test, let's jump to problem number 1. In this problem, we are given this graph of some function. It says that the function is graphed on this domain, -2 to 3. And we can see that it begins at -2, goes till 3. Awesome. First question. On the same grid here, sketch the graph of negative f of x. Now, a common mistake made by people would be this. They look at this negative f of x and they think, that looks like this. But it's not the same thing. So if your brain was telling you that, tell your brain to stop telling you that. This is an inverse function. This is not the same thing. So we are not trying to draw the inverse here. We're trying to draw this. Now, what does this mean? Another common mistake would be to interpret that as this. Now, these are very close. In here, we can see x values becoming negative, and over here, we can see negative applied to the entire function. That means y values becoming negative. So this one here would be a reflection over the y-axis, because imagine all these x values becoming negative. It reflects over the y-axis. So this one is what kind of reflection? All right, I hope you said this is a vertical reflection or reflection over the x-axis because all the y values are being made negative. So that's all you have to do. Flip this whole graph over the x-axis, making all the y values negative. What does it look like? Should look like this. Excellent. All right, 1b. Here we have a, let's see, it says the graph of f, so again, this original function is transformed to obtain a new function g, and the rule is given to us here. G of x equals this. So these things, we can see two things are done to the f function to create the g function. What are these two things? Okay, first of all, whenever you see the function plus or minus a number, that tells us it's a vertical translation, right? It has either gone up or down some units. So we look at this graph here. I'm looking at that and I'm thinking, okay, I'm going to take a point on the original. So I took this point right in the center of the original graph. And I compare where that point is located on the new graph, which is right here. So I'm thinking, okay, that original graph must have translated or shifted down. How much did it go down? If this began on the axis and now we are here, we've gone down about 1, 2, and some people answered this as -2.8. Awesome. Thank you for being so precise. This was really a mistake in printing. I meant for this graph to sit like right on 3 here. But if you wrote that, awesome. You're being very precise. However, if you wrote -3, because this went down 3 units, that's okay also. Okay, now, what does this a do? What's this thing here? We talked about this number at the end, the b value here being a applied to the whole function or the y values, a horizontal shift. Now this a is being applied to the x values. And we know when we put a number in front of x or y, it is a dilation, a scale factor. Okay, so what happened to this graph? Take a look at this graph compared to the original. Which way does it look like it's stretched? Did it stretch left to right, or did it get compressed? Like, did it get, did it get compressed along the x-axis or stretched? What do you think? Well, clearly it was stretched. You can see this one's kind of more upright and this one looks like longer. So it got stretched. By how much? Let's take another point and compare. This point here is at an x value of 2. And now I'm going to look at where that point is here. It is here. And now if we look at the gap from this center point to here, again, this is a gap of 2. And now from this center point to this point, it's a gap of 4. So this was stretched 2 times, right? So the stretch is a 2 times scale factor. However, we should know with x, we're not going to replace the a with 2, we're going to replace it with a half. If we see this thing stretching 2 times wider, we're actually going to put the reciprocal 1/2 in here. Okay, just remember it works with that with x. So now finally, the question is asking what is a and b? Well, a and b are 1/2 and -3. Great, let's go to the next one. Here we have a situation where a line passes through these 2 points, and that line then intersects a parabola, which has a vertex of this and passes through this point. So we have 2 separate things here, a line and a parabola. And that's kind of where the question goes from here. It says, show that the equation for the line is this. So we're ignoring everything about the parabola. We're just looking at what we know about the line, which is it passes through these 2 points, and we need to show the equation is this. Now, a common mistake. Some students might do this. They have their linear equation, which is given to them here, and they're like, okay, I need to show that these points are on this line. So what I'm going to do is I'm going to substitute those points into the equation. So see how 1368 was put in here, 68 for y, 13 for x. And you're like, okay, solve. Oh, 68 to 68. Great. Since they're equal, I've shown that that point is on that line. Yes, you have shown that. But it doesn't say show that these points are on the line. It says show that the equation is this. These are common questions in the IB. They are meant to, basically, you're supposed to do the work to create this equation. But the reason they're giving you the equation is that so when you finish your work, you can check if you were right or wrong. That's all. And therefore, it basically gives you what you're trying to get to. It's telling you this is the goal. Get to this. Do the work that's necessary to get to this, and do the work that's necessary to get to this parabola. Because then in part C, you're going to actually use both of those equations, and it wants you to have those two equations available to you, even if you weren't able to create them. You still have them available, so you can still tackle problem C, and we'll look at that in a second. So let's look at A. We need to create this equation. Well, when we're given 2 points, we can create an equation of a line using this form. This is one of the linear forms we learned. However, for this form, we need 1 point, x1, y1. So one of these coordinates is fine, but we also need the slope. So how about you find the slope first? Okay, so looking for the slope, you need to use both points. Here's the slope equation. I found the slope, it's 5. Now that you know a slope of 5, you put it in here, and then you substitute for y1 and x1, one of the 2 points, your choice, and then create the equation with the line. So here's the work for that. I substituted again the 68 and 13 point in there. There's my slope I just found. Simplifying that, I do get to the equation it gave me. So I've shown that that is the linear equation, and it matches what we have. Let's try B. B says show that the equation of the parabola is this. So again, same way, we continue. Let's go to B, which is the same thing as A, where we're creating an equation, but this time it's for the parabola. Now I want to note that on the test there may have been a typo here. This vertex for the parabola should have a negative 15.5 like this one has. Okay, so let's work with that value. And we're going to do the same thing. We have a vertex of a parabola, and we have a point it passes through. So we know there's different forms of parabolic equations. One of them is the vertex form. Using vertex form, we can put those values in and continue. So just to remind you, vertex form looks like this. It's called vertex form because the h and k represent our x and y values of the vertex. So substitute those values in there, and then substitute the point you know on the parabola, which is this one, into x and y, and that can allow you to solve for A, and then you'll have your equation. Let's try. Okay, so here's the vertex substituted in here. You can see the 1.5 and negative 15.5. This one becomes the opposite sign. And then I put in the point negative 3 for x, negative 2 for y. Kind of went around through there. This one might have been hard because this was paper 1, but let's take a look then real quick. So negative 3 plus 1.5 is negative 1.5. 1.5 squared. I know it's like some of us might grab the calculator for something like that, but think of it as 1.5 times 1.5. 1 times 1.5 is 1.5, and then half more is 0.75. So we get 2.25. So that's what I have here, and we're dividing then this by that. That's an easy division, 6. So A value is 6. There's our function. However, it says show the equation of the parabola is this. This is vertex form. This is standard form. To change from vertex to standard, we just open these parentheses, which I did here, multiply everything by 6, which I did here, and then finally subtract the 15.5. And you do get to this same one here. Great, it works. Okay, so now, like I was mentioning before, these questions are often set up this way, where it gives you your goal here. It gives you your goal here. So even if you couldn't quite get to those equations through these processes, you still have them available to you for question C, which says, hence, by solving through factoring, find the points at which the line and parabola intersect. So we know when 2 curves intersect, we can just, to find those points, we can set them equal to each other, right? So we can say, when does this one equal this one? And we literally just set up an equation, right? Set the line equal to parabola, and by solving that, you will find out when they are equal to each other, when they intersect. So try to follow this process through to the end. Let's see what you get. Okay, I moved everything to one side so that I could have 0 here. Therefore, it can be factored. It actually says solve by factoring, right? This was a paper 1, so you're not expected to use your calculator or anything. So it should be factorable. So I'm factoring here. I get this, and then we have our 2 solutions. Okay, in the end, 10 marks, and not so much in that problem. Testing your some key skills from this unit, making linear equations, making parabolic or quadratic equations, and then solving like this. Okay. Let's go to the next one. So this one, question 3, it says find the values of k for which this equation has one repeated solution. And then B, find the values of m such as this equation has no real roots. Whenever we see this thing about solutions or how many roots or solutions, we know it's a discriminant problem. So let's remind ourselves about the discriminant. The discriminant is b squared minus 4ac. We know when the discriminant is less than 0, in other words, when this thing is negative, we have no real roots. And the parabola will then look like this. It has no x-intercepts. All right, we know when the discriminant is 0, we have one solution. This says one real root here, but this is often called also a double root because it comes from a perfect square trinomial, which still has two factors, but both factors produce the same answer for x, so it could be called a double root. And finally, when the discriminant is greater than 0, that means when the discriminant is positive, we have two distinct or unique different solutions. Okay, for discriminants, and let's look at A. In A, we are told that this equation has one repeated solution. So that's the idea of this one here. One solution, but repeated means like a double solution anytime we have this situation. So discriminant has to be 0. So set the discriminant equal to 0. All right, so now do the substitution of your B value and your A and C values, and let's see what you get. Okay, so I substituted B, which is negative 2k in here, b squared, minus 4 times A, which is 5, times C, which is 6k. Great. Simplifying that a little bit, it can factor. When we get to this point, we can factor it. It's equal to 0. Therefore, we can get two solutions. So when k is 0 and when k is, or when k is 30, if you put a 0 or 30 in here for k, you would have a parabola with one repeated solution. That means a parabola that's with its vertex right on the axis here. All right, let's try B. In B, it says this equation, we need to find the values of m that make this a quadratic that has no real roots. So no real roots right here. Discriminant is less than 0. So begin with that. Discriminant is less than 0. Okay, put in your values for A, B, C in there, and let's see what you get. Okay, so A went in here. B value went in here. A, C. Okay, we get to this point. Now, here is where an error often occurs. All right, a lot of students, they look at this inequality, and we did some lessons on this where we talked about how to solve quadratic inequalities because it's important. They're not solved like linear equations. So some students approach this way. Let's continue over here. So you have this. The 56 went to that side. Okay, great. Divide by 9. Okay, divide by 9. And now you have m squared. So you're like, okay, I'm just going to take a square root on both sides. Done. I got that. When I take a square root, I know I put plus or minus, so I'm done, right? I've solved this problem for m. Well, no. Remember that quadratics behave a little differently when we're talking about inequalities. So let's take a look. This is how we should approach it. First, I'm solving this, and I made it equal to 0 because I want to find out where the x-intercepts are. And then I will go back to the inequality. So I set it equal to 0. I'm solving. So same thing we did here. Solving. I got two answers, plus or minus root of 56 over, I can simplify this, right? Root of 9 in the denominator is just a 3. So that's what I have here. Okay, so those are my two solutions. That means this parabola right here, because that's the one we just solved for, has x-intercepts here, negative 56, root 56 over 3, and positive root 56 over 3. And we know it's a concave up parabola because the a value is positive, so we know it goes like this. And now again, we do a mental or logic check. We say this parabola has to be less than 0. So when is this parabola less than 0? Well, the parabola hits the axis here and here, so it is less than or below 0 from here to here. And over here, it's above the axis, so that would be greater than 0 here also, but here it is below 0. So that means my final answer for m is not this, it is this. From this value to this value, see, from this, and that negative is maybe not very clear there, negative. From that negative value to this positive value, the parabola is less than 0. That is our solution, not this. Okay, that's important. Small point, but important one. Okay, let's go next question. Question 4, this sketch shows part of the graph of a function, okay, with these points on it, and you can verify that those 4 points are the 4 we have in blue here. Now, it says a second function is defined by this. So we're creating a new function, and we're doing some transformations to the original. What transformations are taking place here? That's the question. First of all, what is this x plus 3? What kind of transformation is that? Well, that tells us that we are going to move or translate 3 units left. When we see x plus 3, we're actually moving minus 3 on the x-axis. Great. Now what about this minus in front? We've talked about this in a couple problems. Well, that is a reflection over the x-axis because we're making the whole function negative. That means all y values become negative. That means it reflects over the x-axis. So those are the two transformations taking place there. So all you have to do is apply those two transformations to every one of these points. Let's begin at this point, for example. Okay, we're going to move left 3 units. Okay, so it's going to go 1, 2, 3, end up here, and then reflect over the x-axis. So this one will reflect all the way down to here. So that point was negative 3, 6. And now we moved left 3 and did the full reflection. So it went from positive 6 on the y to negative 6 on the y. So now our new location is negative 6, negative 6. Notice I used a little apostrophe there. That means A primed, or it means the image of A. The image is always the thing that results after a transformation. So there's that one. Let's try one more point that way. So this point here. Okay, left 3 units is going to bring us to, oh, there's the point, 0, 3. 1, 2, 3 units, so I end up here, and then reflect over the x-axis. Okay, so it reflects down to here. There it is. And that point is b prime, negative 3, negative 3. You can continue with the other points, but that's how this question goes. You move the 4 points, and then you connect them properly. So you have to be careful with the connection then. Take a look at this. So here's A, B. Main thing to remember is it was reflected. If this thing was reflected over the axis, it flips over. So this one goes down. It has like a valley here, but in the beginning here, this one has a peak because when you reflect that, it's like the opposite mirror image. So peak. And here is a peak, which becomes a valley. And notice the whole thing has been shifted as well. Take a close look. That should be meant to be a straightforward problem. One thing that also gets students is they're not very careful about how they draw things. Like they get the 4 points, they kind of connect them, but it's a little bit, could be a little sloppy with the curves and so on. So be careful. Like here, when you look at the original curve, between negative 1 and negative 2, you can see it crosses right there, crosses right there. It just passes through there perfectly, like that. And that's what I did here. I made sure it went from negative 4 to negative 5 perfectly. I saw all kinds of drawings, people drawing things all over the place, but you use clues from the original to help you draw the new one. Okay, next question. Express this function in this form. This is a very common IB question. This is one form of a quadratic. This is standard form. And this is vertex form. So let's remind ourselves of the forms. This is standard form when we see the ABC values. This is vertex form, which we looked at already in another problem. This is intercept form or factored form. Okay, we can go back and forth between the different forms. Right now, this question is asking you to go from standard form to vertex form. And there's a very specific procedure we use to go from standard to vertex. So what is that procedure? Well, the procedure is called completing a square, and here we are trying it. Completing a square has us first move the constant to the other side, then factor out the coefficient from the x squared here, then find what we call this a magic number that makes this a perfect square. To find that number, we do b over 2 squared. So 8 divided by 2 is 4. Square that, 16. So that is the magic number we add here, which makes this a perfect square. If we've added 16 here, we have to add 16 here, right? No, yes, we do have to add 16, but there's a 3 here. So truly what we've added on this side is 3 times 16, which is 48. So we have to add 48 here to maintain the balance. We can't just randomly insert numbers unless we keep the balance. Okay, that simplifies to this. We have changed standard form to vertex form. That's what question A wants you to do. Okay, let's look at B. Hence or otherwise, find the coordinates of the vertex. So hence or otherwise always implies you're going to use what you did and you're going to continue on with it and do something else, right? So we have our vertex form. So we know the vertex of this parabola. What is it? Okay, the vertex is negative 4, negative 11. But we are taking this parabola and changing it to a new one like this. So again, these transformations are all over this test. You got to know your transformations. Okay, so to create the new function, we're doing this to the one we see here. And what's going on here? We need to break down these transformations. Here's one way to look at this. One way I think to approach transformations is to look at them and think about what order, what happened first. So let's say we began with just the original function, and then I'm looking at this. I'm like, what happened first? Well, let's start in here. Well, maybe we did this first. So x was replaced by x minus 1. And that tells us a translation 1 unit to the right. Right? And then next, I'm looking at this. I'm like, that isn't quite this. Okay, that x needs to be replaced by 2x. So that x is now replaced by 2x. And what is the effect of that? Well, that is a horizontal dilation, right? It's a stretch or compression along the x-axis. And in this case, this 2 tells us it's going to actually compress, because remember, we always take the reciprocal. It's going to become half its width. All right, great. That doesn't quite look like that. So the last thing, we can now add 5. So I kind of broke down the steps of the transformations here. First was this translation, then a dilation, and then a vertical translation up 5 units. So that's kind of what happened. One mistake that students make here is this, and it's good to point out mistakes. All right, start with the original and be like, I look at this and I'm not thinking x minus 1 first, I'm thinking 2x first. So they're like, okay, 2x happened first. X was replaced by 2x. That's fine, we could do that, but it leads to a problem now. So if that was done first, then the next thing we need is x minus 1. So that x is replaced by x minus 1. And anytime we do that replacement, we need the parentheses. If that x is replaced by x minus 1, it looks like this. If you multiply that, that is not the same as this. So this is the proper sequence of transformations. This is not, because it brings you to a different place. So it matters which of those things on the inside you do first. And I hope you can see why here. So translation first, then dilation, and then the vertical translation. Okay, but all of that is, I mean, that's one way to find, because your goal is to find the vertex of this new function. So you could say, okay, I know the vertex of this function is -4, -11. Oh, we said this order is the proper order. So why don't we apply these transformations in order to the vertex? We know from this equation here, the vertex is -4, -11. First thing that happened is we have a translation 1 unit to the right. So if this moves 1 unit right, the x value changes to -3, right? We moved 1 unit to the right. Okay, next, the x became a 2x. So 2x was substituted in. That is a horizontal dilation. And that tells us that all x values are not doubled. They're made half of what they were, because it's always the reciprocal of that. So that x value is -3. It is now going to be half of that. It's -1.5. Y has not changed yet. Finally, now we change y, because now to this, these are changes of x, and now this is being applied to the entire function. We move up 5 units. So this y value up 5 units becomes this. There's our vertex of g of x. That's one way to approach it, to break this down and look at the order of transformations and apply them to the vertex we know. Another way is to simply take this and put it into your function, because this tells us that this goes into the f function. So let's take a look. That's what we're told. And now we're going to take this function here, or this form, either form. I think I take this form and just substitute that in, right? This tells us that into the function, we're putting 2x minus 1. So that x is replaced by 2x minus 1. And then we add a 5 to the entire function. So we can put a plus 5 at the end here. So here's how we do that. Here's that 2x minus 1, replace that x. We have that. Now we have this 5 added here. Okay, those are the two things that are happening here, that are shown here. Now simplify this. Okay, that becomes 2x plus 3. We have a -6 there because these combine. And now this one's a little trickier. That's why this approach might be easier. It's a little tricky here because usually we don't see quadratics presented in this form. Because normally we look at it and we say, hey, the vertex, it would be -6 for y value and a -3 for x. Well, not in this case because this 2 is here. So here's what we have to do. Factor out the 2. And now we have this. So this is actually the x value of the vertex right here. And remember, it's always the opposite. So -1.5 because this is positive 1.5 and -6. So there's our vertex from this approach. And there's the vertex as we change it step by step. Both ways work. Both are great approaches. Pause and make sure you understand. Okay, let's try question 6. A parabola has these x-intercepts and passes through this point. So again, this is one of those problems where we're told something about a parabola, we think about the forms of parabolas, and we see if we can make an equation, because it says find the equation. So this, looking at the forms again, if we are given the two x-intercepts, we know we're going to look at intercept forms. So let's use intercept form, put these two values in there. So there's intercept form. Substitute for p and q the proper values based on this. Okay, it should be that. And then substitute the point you know. So 40 for y and 8 for x here and here, or sorry, -8. And now this will allow you to solve for a. So just change this to a number, divide 40 by that. Let's see. Okay, a works out to 4. So therefore our parabola is this. Excellent, that's a. In b, it says to obtain g of x, another parabola. So again, transformations is just never ending in this unit, right? In this test here, because we need to know transformations. So let's take a look at this. To get g of x, we take the f of x function, the one we have here. We translate it 2 units left, 5 units up. Okay, 2 units left, 5 units up. So that means we have to take the f function, 2 units left, we put x plus 2, and 5 units up. So we're doing this to our function, right? Okay, and then it is reflected over the y-axis. Okay, so then reflected over y-axis, the x is replaced by negative x, because to reflect over the y-axis, we're making all x values negative. So that's why we substituted negative x for that. So there's our transformations. So you can now simply do these substitutions into here, right? F of x, so this x here is replaced by negative x plus 2. Every time we see x here, which is here and here, we replace it with negative x plus 2. And then we add a 5 to the entire thing. Let's take a look. So here's my g of x function. It's my original function with these changes made, these transformations. So see that x has been replaced by negative x plus 2 here and here. And the 5 has been added at the end to the entire function. Simplify, and you will have your g of x function. Okay, simplifying that, check your work here. The negatives and positives matter here. Simplifying, this multiplied here, and then there's a 5 at the end. It becomes this, because it wants you to show that it's this standard form. So you need to multiply everything through. Check your work carefully. Let's go on and look at number 7. Here, we are given a rational function. So now we're moving away from quadratics for a moment, looking at rationals, which take on this form. And we were told it has a vertical asymptote of x equals 3 and passes through this point. Vertical asymptote, remember, is determined by looking at the denominator of your rational function and setting it equal to 0, because we cannot have a denominator that is 0. So we solve for, see what that gives it that, right? So we can begin there, yep, and say 4x minus p is equal to 0. Set that equal to 0 and solve. We know, however, that the x value is 3, right? So we know if I solve this here, x is 3, I put that in here and I get a p value of 12. So I could have put x is 3 here right away and found p is 12. Anyway, p is 12 based on this hint here. Okay, now that we know that, we can rewrite this function using a p value of 12. So we're getting closer to having all the pieces we need. We have p, now we need q. So to find q, we're going to use the other piece of information that's given, which is that this rational also passes through the point 4, 6. So now we know an xy coordinate, and we can replace x and y in here with those values and solve for q. So let's try. Okay, so here's our equation with the p replaced with the 12. And then I put in the 6 and the 4 given here for x and y, 6 and 4. Solving that, we can get a q value of 5. Okay, so now we know p and q, and now we can go on to step B here, which says, well, you have your rational. We know that we can have rationals in this form or in this form, and the way to change that is to combine these two here. So this second part, the q value, which we now know is a 5, we know to combine these fractions, we need to take this second fraction, which is really 5 over 1, multiply by 4x minus 12 over 4x minus 12, a version of 1, and we will then have a common denominator we can combine. So try that, finish it off. Okay, check your work. Multiplying 5 times that gives us this. Combine things, you get to here. Okay, let's look at 8. 8 says you pay a one-time 35 euro membership fee, followed by 6 euros per month for a music streaming service. Okay, one-time fee and then 6 euros per month. Okay, this is very much like the problems we've looked at recently. We need to write a function c of m for the average cost to you per month. Okay, c of m, the average cost to you per month. All right, so average means what is the total cost divided by how many months, right? So let's try. Here we go. Average cost is your starting fee plus 6 times however number of months you do. That's your total cost. And then you divide by m because it's an average. And that can simplify to this. All right, both forms are okay. Now that we have this, we can sketch it. We should know how to sketch rational functions. Rational functions, we first look at the denominator. That gives us our vertical asymptote, right? But we can also find more. Sorry, I just popped it up there. But what about x and y intercepts? How about finding those? So x intercepts are when y is 0. Y intercepts are when x is 0. So let's take a look at that. X intercept, we made y 0. And I'm solving here. And I solve for this. Because the term sketch in IB exams means, yeah, you're going to do kind of a rough sketch of the graph, but it needs to have some details. And having x and y intercepts and asymptotes and things, those are important details. So I found the x intercept to be this. And the y intercept is found when x is 0. And in this case, when x is 0, we know this doesn't work. We can't divide by 0. So I put here dne means does not exist. There is no y-intercept. Okay, so now what about finding the asymptotes? So we know, again, the denominator tells us the vertical asymptote. So what is it? And what is the horizontal asymptote? So vertical asymptote, m equals 0, because when m is 0, we have 0 down there. That's the vertical asymptote. That's also why this y-intercept doesn't exist. And the horizontal asymptote, you may remember the rule is you look at these and you do 6 over 1, because there's like a 1 here. So there's our horizontal asymptote. Or if you look at this form of the rational, well, we can see the vertical shift right here, 6 units up. And that tells us where our horizontal asymptote is here. Great. So the sketch looks like this. The whole rational function shifted up 6 units. We can see here's that horizontal asymptote. And we can see the vertical asymptote at 0 here. And here's part of the curve and part of the curve here. And the question said, explain what the asymptote represents. Well, it was kind of referring to this one. It should have said horizontal asymptote. But basically, we can see the average cost per month is approaching 6. It will never get there, but it's approaching it over time. Because as you have more months with this service, that 35 euro initial fee will be spread out. You can think of it being spread out over the many months that you remember. So that 35 in month 1 is a big part of what you pay. But later on, it's a smaller part. So your average cost is close to 6 with that monthly fee. And we can see that in this form of the equation as well. The 35 is divided by all the months, and then you add 6. That's what you pay every month, right? Okay, so that's your average cost. All right, paper 2, calculator is now allowed. We're looking at this question, and we have a very common kind of quadratic area problem. We have some kind of a rectangular garden. It's divided into 2 halves here by fences. These are all fences around it. We know we have 460 meters of fencing for this whole thing. All right, so you want to find the dimensions of the rectangle given that the area will be maximized. So if we're going to do a maximum area, well, maybe you're thinking I need an area formula. And if that area formula is quadratic, the maximum of that quadratic will be the vertex. So why don't we proceed in that way? First of all, let's label some of these. I'm going to call this x, and then therefore this is x and x also, and y for this length and y here as well. Okay, so what's the area? Well, the area is just x times y, right? This times this, base times height. So there's the area. However, this has 2 variables on this side. We need an equation that's only in 2 variables in total, right? We have 3 variables here in total. So we need to replace the x or y and create a new equation. We replace them by thinking of more information we're given, the 460 meters of fencing. So that means all these lengths here combined make 460. So what equation can you write for that? How about this? 3x plus 2y equals 460, right? That's all the fences. 3 of those, 2 of those. All right, simplify this. I think I solved for y, so I'm going to ask you to do the same thing here. Rearrange this, solving for y. All right, here goes. Move the 3x over here, divided by 2, I get this. Now that can be resubstituted in for this y here, and we will then have an area model using only the variable x. So do the substitution and then multiply through and simplify. Let's see if you get it. Okay, I've substituted the y here. Now I multiply this, I get this quadratic equation representing the area. And since this is quadratic with a negative a value, it's concave down. So imagine a parabola that's going down like this, like a hill. And that hill has a maximum point, and that is your maximum area, because that a is like your y value, that's your maximum area, right? So find the vertex of this. And remember the formula negative b over 2a to find the x value of the vertex. Try it now. All right, so the vertex is this. So that means when x has a value of 76.7 meters, this area will be maximized. So now that you know x, find y. You can use this equation, put that in there and see what you get. Okay, putting it into the equation for y, I found this for y. So y is this, and x is this. And those are the only exact measures we can have here for this area to be maximum. Change those measures even a little bit, this area will no longer be maximized. All right, question 10, the long response, 24 big marks. Lots of stuff here, combining all the stuff we did with quadratics and linear equations, everything. And also kind of a deeper conceptual understanding in terms of applied problems. Let's try. So a student discovers that his dad's old shirts are now super valuable as vintage items. Selling the shirts online at 45 euros each, he is able to sell 64 shirts per day. So he already knows that. The price is 45 euro. He sells 64 per day. That price leads to this kind of business for him. 64 shirts sold. However, he estimates that for every price increase of 7 euro, so he's thinking, hey, what if I increase this by 7? Then it'll go up to 52 euro. Okay, and then increase by 7 again, up to 59 euro. So for every increase of 7 euro, he will sell 3 fewer. So that's the thing. When you're running a business, you have to consider that. I can do higher price. And in this case, the higher price leads to fewer shirts being sold. That makes sense because maybe some people don't want to pay more. So you have less customers now. However, there's a trade-off in business. You can raise the price. And if your sales don't go down too much, you're still making more money in total, right? So that's what we're going to figure out here. And we're going to create a revenue model, profit model, and so on. Okay, so if X represents the number of price increases, write an expression for the price after X price increases. That is simply this, 45 plus 7X. Why? Because 45 is the original price, and then you add 7 for every price increase for X, right? So if you put an X equals 2 in here, that would be saying like 2 price increases, and then the price would be 2 times 7 plus 45 up to 59, right? Okay, so now do the same thing with an expression for the units sold. And remember, in the beginning, he sells 64, but what happens to his sales when he increases the price? Well, we have this, right? His initial sales are 64 shirts, but then it goes down by 3 for every price increase. So there's those two expressions. And notice it said expression here, write an expression, write an expression. Expression looks like this. There's no equal sign. If it said write an equation, then you could have written like, you could have written a variable representing your, here, for example, your price equals, right? But it says expression, so that's good. Now show that the revenue as a function of price increases is given by this function. So it's just like those problems before where it says show that you're given the equation you're trying to get to, and you have to show that you can get there. And that's basically saying we're going to give you the equation in case you can't make it happen here. You're going to need that equation to do further work. So here it is. Here's the equation for you, but let's see if we can get there. So we know revenue is the money you make in a business, right? So like the money that's coming in, all right? So units sold times price. That makes sense. How much you sell times the price of those things is your revenue. So multiply these two expressions to get your revenue model. Okay, so multiplying them through, and then you get to that revenue model. Great. So now it says take your model, which is this one we created, the revenue model, and state the y-intercept. We know this is a quadratic in standard form, so the y-intercept is actually when x equals 0. Okay, when x is 0, that becomes 0, that becomes 0. We're left with just this number. So that's our y-intercept. And what does that y-intercept, describe what this point represents. What does that mean? Well, look at your model, right? X represents the number of price increases, R represents the revenue. So this means when there are 0 price increases, the revenue is this, right? So this represents the revenue with no price increases. This is how much money this person's making per day if no price increases are applied. Okay, next, find the vertex. Okay, standard form, vertex, therefore we're going to use negative b over 2a. Try that now. Okay, that gives you an x value of 7.45. So it says this revenue will reach a vertex with 7.45 price increases. Okay, we have the x value. What about the y value? So put that into here and find the y value. That gives you a y value of 4,046.3. And what does that represent? It is the maximum revenue because the vertex is a max point. So maximum revenue of this amount, right? This is your revenue with 7.5 price increases. Okay, finally, find the x-intercepts. When you're looking for x-intercepts, you always set equal to 0, right? And then solve. This is paper 2, so I would suggest use Poly Simulation, your app, to solve for this. All right, so using Poly Simulation number 2, we get 2 x values, this and this. Those are our x-intercepts. What do those represent? Well, again, x represents the number of price increases, but in this case, we made y, or we made the revenue 0. So we're saying these are the number of price increases that lead to no revenue. So in other words, if this person did 21.3 price increases, the price would be so high, they would have no revenue left. And that means basically nobody would buy a single shirt, right? So those are the revenue of 0 at these price increases, right? Okay, now sketch the graph. So we had this equation, we just found key points. This is how we sketch quadratics, right? We have the y-intercept, we have the vertex, which we just found, we have the x-intercepts. So why don't we just put them in there, right? X-intercepts, y-intercept, vertex. There's our revenue model. And you can see There's our initial revenue with no price increases. And we can actually ignore this part of the graph because we're not doing negative price increases. Or you could think of that negative price increases, right? You're actually lowering the price by 7, lowering. That makes sense. Okay. Anyway, revenue goes up at 7.45 price increases. It's the maximum revenue of this. And then the revenue goes down because after that, even though you're charging more, there's less people, less buying, and it works out to less revenue in total. And finally, here's no revenue when you do so many price increases. Okay, great. There's the graph. Next, there are costs associated with a small business. Costs will be €3,700 when 2 price increases are added, and costs will be this much when 17 price increases are added. It should have noted here that the costs follow a linear trend, but that's kind of the assumption we can make here. We were given 2 points. 2 price increases leads to this cost. 17 price increases leads to this cost. Okay, so you're given 2 points. You want to make a linear equation. We did that earlier. You're going to find the slope first, and then you're going to create a linear equation. So the slope can be found like this, and then putting into the y minus y1 equals mx minus x1 form, we can create our linear equation. And I think I rewrote it like this because I want to write c of x. So cost based on x price increases is this. And you can see with a negative slope, the costs are actually going down. So as you kind of expand your business, your costs are going down. That makes sense. All right, sketch this, add this sketch to your graph. Well, what's the easiest way to do it? Well, we had this graph already. The easiest way to sketch a line is to just put a couple points on your graph and connect them because a line will pass through the 2 points that are on it, right? So we have these 2 points, 3,700, which is here. And we have the point 17, 2,620, which is here. Connect those, that's it. We've made a line. It's so easy. You don't have to worry about using slope here and y-intercept. It's so much easier just to have 2 points, connect them, done. And we had 2 points right here. There's our cost line. You can see costs are decreasing, right? Okay, so there's what that looks like. Great. Let's go on to the next part. Finally, we're making a profit function. So we have the revenue, we have the costs, and now profit is revenue minus costs, right? Revenue minus costs. So why don't you take your revenue model, subtract the cost one, and see if you can create the profit model. Okay, here's the revenue model. Here's the cost model, and you're subtracting. This is very important. I have parentheses here. That minus applies to both of these. Simplifying, get to this. Double check, make sure you can get there. There's our profit model. And then it says add the profit to your sketch. Well, to graph it, we need the easiest would be to find the x-intercepts and the vertex, then we can graph this profit because this is also quadratic. So why don't we get the vertex and x-intercepts? So the vertex I found here, 9.2800 there, and then solving here, making it 0, find the x-intercepts, these 2 points. So with the vertex and those 2 points, we can graph it, right? Here's our profit model, and you can see the vertex there. Here's the 2 x-intercepts. So now, final step is to show how the profit model corresponds to the revenue and cost models. And we talked about this relationship. It's very important to understand what's going on here. We can see here, this is the profit model. So here's 0 profit. Here's maximum profit of 800, right? And here's 0 profit again. So we want to go to maximum profit. So we can put a line there. That's the maximum profit. And when you extend that line up to revenue and costs, you should clearly see the relationship. Here's maximum profit. So this gap here shows us that profit of 800 from here to here. Now, when you look at the difference between revenue and costs, if you actually found this value, which is about 4,000, and this value, which is about 3,200, that gap here is also 800. So this gap here matches this one exactly because profit is the difference between revenue and costs. And that's the relationship you were meant to comment on in this question here. Okay, solve the, let me go back for a second. And then here, profit is 0. Why? Let's go back right here, because here at that moment in time, revenue and costs are exactly the same, therefore no profit. And likewise over here, revenue is more. And by the way, since this is the maximum profit, this is the maximum gap you would be able to find between these two curves. And here, revenue is going down because again, too many price increases, not many people buying your shirts anymore. And then costs here, and then revenue and costs are equal again. So then 0 profit. After that, costs are higher than revenue. So we can see this goes negative profit, which actually means a loss. You're losing money. Same here, losing money. Okay, final thing, solve this inequality. Revenue greater than cost. So you are just setting up your revenue model greater than this one here and solve this inequality. So it's going to be a quadratic inequality. And let's check our work. Moved everything to one side. Don't forget when you have a quadratic inequality, there's that whole process of, okay, this is a parabola. We know the solutions to this one already because this is actually your profit model, right? Revenue and costs. When you subtract that, move that over there. it's like revenue and costs, right? Revenue minus cost, which is profit. This is our profit model. And our profit, this is basically saying, when is revenue greater than costs? Well, that is when profit is greater than zero. That's how these become the same thing. Profit is greater than zero because it represents when revenue is greater than costs. And that happens from here to here. So again, going to our graph, we knew that the profit went here from about 3 to about 15 here, right? 15.3. That's when we had profit. And we were just answering the question of when revenue is greater than costs. Well, revenue is greater than costs from here to here, from 3 to 15. So that's our final answer here. From about 3 to 15.3, this represents when profit exceeds zero. In other words, when the business is making money. Great job. I hope this helps you if you struggled with some things on the test. There's more you can do. I have videos like this for similar recent tests from a recent year, and that's your next task. Try another recent practice test, and you will have videos that can guide you through those as well. You can do it. See you soon.